Geotechnical Site Evaluation and Stability Analysis of a Tailings Dam, a Case Study. Abstract: the safety of tailings dam is of great concern because of how catastrophic their failures can be. This project was conducted to ascertain the stability of a proposed tailings dam. The geotechnical properties of the designated construction site and the building material were tested for. A two-dimensional model of the proposed tailings dam was then developed with the use of GEO5 Geotechnical Software Suite. The geotechnical parameters obtained from the laboratory testing was inputted into the developed model. A finite element method, FEM, of analysis within the GEO5 Geotechnical Software Suite was employed to perform a slope stability analysis, steady-state seepage analysis as well as a consolidation analysis to assess the long-term stability of the tailings dam. From the analysis, the factor of safety of the dam was 1.88, which means the dam is safe. Steady-state seepage analysis revealed that the dam was safe from undergoing failure by hydraulic fracture or internal erosion. The consolidation analysis revealed a settlement value of 28 mm, which means the foundation was strong enough to hold the tailings storage facility without undergoing settlement above the allowable range. Keywords: tailings dam, stability analysis, finite element method, dam modeling, site evaluation. Introduction. Tailings dam, also referred to as tailings storage facility, TSF, is a very important engineering structure in the extractive companies. Large quantities of waste in the form of slurry are generated in the processing of ores to extract the main mineral of interest. These wastes generated from ore processing happens to be environmentally hazardous due to the reagent, chemicals, that are introduced to aid in the extraction. These wastes are therefore directed to and stored in the tailings dam. Globally, quite a number of catastrophic incidents of tailings storage facility failures have been recorded. A few include the TSF failure at Vales Fe.O iron mine in Brumadinho, Brazil in January 2019, resulting in over 300 deaths. Another one is the Samarco TSF failure in Brazil, in the year 2015, which resulted in 19 fatalities, and then the tailings dam failure at MT Poly mine in Canada in 2014, which caused significant environmental damage. 5. There is therefore the need to perform laboratory tests to define geotechnical parameters of the building material in order to perform stability evaluation so as to safely design and construct these facilities to withstand the test of time. It is in light of this, the paper seeks to conduct engineering studies to assess the properties of the soil material and perform stability evaluation on embankments and foundation for the purpose of constructing a tailings dam using the finite element method, FEM. FEM is one of the most effective and applied numerical methods in the simulation of the time-dependent, anisotropic, and nonlinear behavior in advanced soil and rock mechanics. 2. Geological information about study area. Wassa Abrashia is a town in the Wassa Amenfi East municipality of the Western Region, Ghana. The project lies along the western flank of Ashanti Belt, which is one of the northeast-southwestern, NESW, trending Birimian volcanic belts exposed in southwestern Ghana. Most of southwestern Ghana is dominated by metamorphosed rocks of the Paleoproterozoic age, which fall mainly between the ages of 2300 and 1900 Ma 3. The immediate concession area is underlined mainly by metasediments of the Paleoproterozoic Birimian FLYSC age type consisting of dacitic volcanic clastics, grey wax plus argillaceous, philitic, sediments, intensely folded, faulted and metamorphosed to the upper green schist facies. 9. Numerous small basin-type granite bodies are reported to have intruded the sediments along several regional structures. The shape of the intrusions varies from nearly ovoid plugs 200 m to 400 m long by 40 m to 150 m wide to relatively long, plus 2000 m, and narrow, 50 m to 100 m, sills or dikes. 9. Fig 1 shows the geological map of the area. Fig 1 geological map of the study area. 3 materials and methods used. Careful and detailed field and laboratory tests were carried out to determine the geotechnical properties of the material at the proposed tailings dam site. Geotechnical laboratory works carried on soil samples are herein in accordance with standard protocols for soil mechanics studies. The procedures and techniques employed in these studies conform to the performance criteria, detection limits, accuracy, and precision, as outlined in the 8 Protocol for Mechanical and Index Methods for Assessing the Properties of Soils for Engineering Projects. The British standard for the determination of geomechanical properties of soils for civil engineering projects were employed for the analysis. At all times, laboratory procedures were optimized during analyses to assure the quality of data. Results relate only to the selected samples tested. A field and laboratory works. Surface and subsurface conditions were explored by excavation and logging. In situ test, known as dynamic cone penetration test, DCPT, was also performed. 2 samples each, a disturbed and an undisturbed, were also collected from 5 sampling locations between the depths of 25 cm to 300 cm and conveyed to the Geotechnical Laboratory for analysis. 8 laboratory tests were performed on each of the samples collected in order to evaluate the index and engineering properties that influence the performance of the proposed tailings dam. These include the following. B. Modeling of the proposed tailings dam using Finite Element Method, FEM. The Finite Element Method is a versatile numerical method which was developed to solve problems related to the concentration of stress in continuum mechanics. This method also accounts for the heterogeneities of materials under study, irregular geometries, nonlinearities as well as complex boundary conditions too. It is the most applied numerical method in the simulation of the time-dependent, anisotropic, and nonlinear behavior in advanced soil and rock mechanics. The guiding principle of this method is to divide the section of the problem into subsections, which is termed finite element. These subsections are analyzed individually before they are assembled to generate a global solution to the problem. The generation of the finite elements which can be addressed individually enable this method to account for heterogeneities and nonlinear stress-strain behavior as well as stress-pore pressure variations. GEO5 FEM program allows for the modeling of various types of problems and analyses. These modeling and analyses are carried out in various stages. The first stage is the topology stage and then subsequent constructional stages 6. In the topology stage, a two-dimensional, 2D, model of the tailings dam and its foundation was developed. In order to find a balance between cost and safety, an angle of 26.56 degrees was used for both upstream and downstream slopes in developing the model. An embankment height of 5 m was considered for the modeling of the dam. The geotechnical parameters of the soils were assigned to the various soil interfaces in the model. This was then followed by a generation of the finite element mesh. Fig 2, a generated mesh of tailings dam model. For analysis and discussion of results. A dynamic cone penetration results. Results from the dynamic cone penetration test is presented in the graph of depth of penetration against bearing capacities in Graph 1. Graph 1 depth against bearing capacity. A general rule of thumb is that bearing capacity generally increases with increasing depth. From the Fig 4, however, the plot of bearing capacities against depth is not entirely continuous. This depicts heterogeneities within the soil layers in the subsurface. Averagely, the deviation from a regular downward increment in depth and bearing capacity is minimal, and therefore there is no need for deep excavations and reinforcements for the tailings dam foundation. B. Logging of excavated sample pits. Results from the logging of the sample pits are described individually in Table I, and the general profile is presented Fig 3. From the logging of the 300 cm deep excavation of the sampling points, 2 main layers were observed. The first observed layer of a 25 cm thickness was identified as the top soil. This layer was black to brown color, humus, which was mostly sandy to silty grain loose material with moderate moisture content. This layer needs to be stripped off before beginning the project. The second layer, which happens to be the subsoil, lies between 25 cm to 300 cm depth. This layer was made up of a pale yellow phylitic soil which is silty in nature. Groundwater was encountered at an approximate depth of 200 cm beneath the loose phylitic subsoil was a grey to white colored transitional material. This layer is believed to be phyllite, parent material. This layer was found at an average depth 300 cm. Fig.3 Profile of the subsurface layers of the area. See moisture content, specific gravity, and falling head permeability test. The summary of results obtained from the moisture content, specific gravity, and falling head permeability test are presented below in Table 2. It can be observed that the soil has a normal specific gravity of natural soils, moderate permeability rate which is characteristic of sandy silt soils. Water content is low, which means the soil properties are not going to change much with water. Hence the soil is not problematic. D. Atterberg limits test. From Atterberg limits results in Table 3 it can be established that the soil in the study area has an intermediate to low plasticity, and this is as the result of small quantities of clay within the soil. This means the soil has low expansive nature. E. Particle distribution analysis. From the particle size distribution curve plot for the various samples, the soils from TP01, TP02, TP04 show a well-graded fine soil. TP03, TP05 also showed a well-graded coarse soil. From the percentages of the various particle sizes, the soil sample can be referred to as a sandy silt according to the British Standard Soil Classification System. The relative percentages of clay, silt, sand, and gravel are presented in Table 4. F. Standard Proctor compaction test results. From the compaction results in Table V, the soil was found to be of an average unit weight, of 16.91 kN/m3. An average maximum dry density, MDD, of 1.795 g/cm3 can be attained at an optimum moisture content, OMC, of 13.6%. G. Result of direct shear strength test. Direct shear test revealed that the soils in the area had average shear strength parameters of 11.98 kN/m2 for cohesive force and 23.89 degrees for internal frictional angle. This suggests that the soil has a moderate to high shear strength. H. Modeling and analysis of tailings dam. The Finite Element Method analysis tool within the GEO5 software suite was used in the analysis. Analysis of the tailings dam model was done using the Moore-Coulomb approach. The embankment was analyzed completely and homogeneously using the result from the laboratory tests. Table 7 shows a summary of the soil parameters that were used in the analysis. Slope stability analysis. The stability analysis result is shown in Fig.5. The factor of safety was found to be 1.88. The failure surface in the resultant displacement mode is seen to be towards the upstream of the dam. Since the factor of safety is 1.88, which is higher than the accepted value of 1.51, it can be considered as safe. Fig. 4 Slope stability analysis of tailing dam. Steady-state seepage analysis. Another factor that normally causes dam failure is hydraulic fracturing. This occurs when the phreatic line within the embankment daylight into the downstream side of the dam. From the steady-state seepage analysis in Fig. 5, the phreatic line within the embankment seems to reduce gradually and water flow out through the existing groundwater table after long period of time. The tailings dam therefore can be considered safe from failing through hydraulic fracture. Fig. 5 Steady-state seepage analysis of the tailing dam. Consolidation. Consolidation or settlement is also an important factor during the construction of huge structures. Soils with high settlement value may end up causing instability of structures built on them. From the consolidation analysis considering a period of 10 years, the maximum settlement value was 23.8 mm as shown in Fig. 6 below. Upon the increment of the number of years, no further increase in settlement value was noticed. The value of 23.8 mm is considered to be within an acceptable settlement range. The bearing capacity of the foundation soil can therefore be considered high enough to withstand the weight to be imposed by the tailings dam. Fig. 6 Consolidation analysis of the tailing dam. V. Conclusion and recommendation. A. Conclusion. From the research results, it can be concluded that the soil had a good shear strength. Geotechnical logging to a 300 cm deep excavation revealed that the site is heterogeneous. The soil material was a sandy silt type with an intermediate plasticity and an average permeability of 0.0257 m/day. Slope stability analysis gave a factor of safety of 1.88, which indicates that the soil is safe to be used for the construction of the tailings dam according to standard protocols. Consolidation analysis showed that the foundation is strong enough to hold the dam while undergoing minimal settlement, which is within the allowable range. Steady-state seepage analysis indicated that the tailings dam can resist failure through internal erosion and piping. The tailings dam project would be safe to be constructed on the designated site. B. Recommendation: plastic liners such as high-density polyethylene, HDPE, should be used to line the upstream slope face. This will prevent any future problems related to seepage in the case of further tailings dam raise because of the uncertainty in geotechnical properties of the soils that will available for the future raise. A three-dimensional, 3D, slope stability analysis of the tailings dam should be performed to complement the two-dimensional, 2D, analysis, which generally provide conservative results. With higher factor of safety expected in 3D analysis, a more cost-effective slope may be designed while maintaining adequate stability. Acknowledgement: I would like to express my gratitude to my supervisor Edmund Asare, who gave me the opportunity, guidance, and funding to do this research, which introduced me to a lot of new knowledge. I am really thankful to him.